Hello, welcome back. Here we're going to handle a continuation of the vectors. So today we are going to handle we're starting with the dot product. So we have dots. Another name for dot product is the scalar product. So we're going to say A, the dot product of A and B. Is the same as, so if you have A1, A2, A3, those are the components of A, and now we are assuming that the components of B are B1, B2, B3. So we're going to get A1, the same way you are adding, you're going to use to go step by step. A1, B1, A2, B2, A3, B3. So we have plus A2, B2 plus A3, B3. So that's basically dot product. So for example, and remember you cannot work with vectors in two different dimensions. For example, if we have V is equals to 6, I minus 8G, and then we have W is equals to 2I plus 3J. So you're asked to find the dot product. Find the dot product. So our solution, so this is our quiz here. So the first step here is to represent this vector, represent this equation in vector form, and then the other part are now you. So our V is going to be 6, negative 8. Our W is going to be 2, 3. So if we have V dot W, we're going to get 6 times 2 plus negative 8 times 3. That becomes 12 minus 24, which is negative 12. That's the dot product. Another example, you're given A. So here let's just wrap that. So we have A is a vector A is in 3 dimensions. We have 2, 0, 3. We have vector B, which is 3, 4, 2. If you want to find A dot B, you're going to get 2 times 3 plus 0 times 4 plus 3 times 2. So that is 6 plus 0 plus 6, which gives you 12. And dot product or scalar product is a scalar quantity, meaning it doesn't have a direction. And then we have a formula. So we usually say that A dot B, we have said it's equals to A1 B1 plus A2 B2 plus A3 B3, which is equals to, this is called the cosine. No, let's just maintain our small letters. Cos theta. So this simply means that A let's maintain. We have A B will be equals to this doesn't have is equals to A B cos theta, meaning you can get the angle if you want. So I'm going to have cos theta over the magnitude. So by theta you can easily get the angle. So that's how it goes, and this is a theorem that can be easily proved. So our proof for that theorem, we are leaving it for our reader. Next we are going to the next aspect, and our next aspect is, previously we looked at two angles are parallel if we get, if it can be written one in the form of another as a scalar of another. But then how about they are perpendicular or orthogonal? So two angles are, let's say, perpendicular. Other authors prefer using orthogonal. So perpendicular or orthogonal vectors. So two vectors are perpendicular only if the angle between them is 90 degrees. So the angle between them is 90. That makes it them perpendicular. So but our formula is AB is equals to A B cos theta, meaning our AB should be equals to 0. That's the only time we're going to get them to be perpendicular. So that's, we're going to our next, and our next is we want to get the angle, an angle between two vectors. We want to get a real example. So here we are going to use examples to demonstrate. So we are solving two examples. We're saying one, you're given A to be 2I plus 3J plus 2K. Then we have vector B is I plus J plus 5K. So you're supposed to find two things. Number one, Roman 1 is supposed to find the dot product, and Roman 2 you're supposed to find the angle between A and B. So our dot product is quite a simple one. We already know the formula. This one will be A1 B1 plus A2 B2 plus A3 B3. So our A, vector A, can be written as 2 3 2. Vector B 1 1 5. So if we say AB, you're going to get 2 times 1 plus 3 times 1 plus 2 times 5. That gives us 2 plus 3 plus 10, which is 15. It's a scalar quantity. So our part B wants us to get this was our Roman 1. So for our Roman 2, we have previously said that cos theta is equals to let's just remove this and start afresh. So we have our formula states that AB is equals to A B cos theta. So that means we found that cos theta is the dot product over the magnitude of A magnitude of B. So our first step, we already have AB. Our AB is here, it's 15. So the only thing we have to forget is the magnitude of A and the magnitude of B. So we have our magnitude of A is equals to square root of our vector A was 2, 3, 2. You can see it here. Our vector A was here. So we have vector A, we have vector B. So our vector A will be 4 plus 9 plus 2, because it's A squared plus it's A1 squared plus A2 squared plus A3 squared, then the square root. That's how we get the magnitude. So we're going to get root 17. And now we have magnitude of B, which is the root of 1 plus 1 plus 25. You're getting root 27. And now our theta, so our cos theta is AB, which is 15 over root 17 root 27, which gives us 0.7468. But now theta is cos inverse of 0.7468, which gives us 41.68 degrees. So that's how we get the dot product and the distance and the angle between. So another question is show that determine whether the following vectors are orthogonal. So that's our example 2. Determine whether the following vectors are orthogonal. And we say that orthogonal means 90 degrees. They form 90 degrees when you join them. So our first vector, we're going to do one, the other one will be left for the reader to try. So this is our vector A, this is our vector B, then we have another vector here. So we have vector U, is 2i minus j, v is minus a half I plus a quarter j. So we're going to handle Roman 1 and Roman 2 is left for the reader. So remember our formula stated that A and B are orthogonal if A dot B gives us 0. So you're going to get A dot B, it's going to be 6 times 2 plus negative 2 times 5 plus negative 1 times 2. And that gives us 0, meaning they are perpendicular or orthogonal. So our reader will attempt Roman 2 and determine whether it's orthogonal or not. Our next, we're going to handle the scalar, no, not scalar, we're going to handle the cross product. So you want to see on cross product. Cross product, so we are going to have A is A1, A2, A3. So we are defining our vector B to be B1, B2, B3. So if we want to get our cross product, we're going to say A cross B is equals to, so you're going to write a matrix. Here we have I, J, K, A1. So if it's A cross B, you start with A1. If it's B cross A, you start with B1. So you have A1, A2, A3, B1, B2, B3. So we want to get the cross product. Basically what happens here is you delete row 1, you delete column 1, you get a matrix. So that is coefficient of A. So we're going to get A2, A3, B1, B2, B3 minus. So since we are using, if you're using row 1, we have plus, minus, plus. If you're using row 2, minus, plus, minus. If you're using row 3, it's plus, minus, plus. So it's starting with row 1 because we want I to be on the outside. So minus J. Here we delete row 1 and we delete column 2 where the J is. So if you delete, you're left with A1, A3, B1, B3 plus we have K. So here we delete where K is. Sorry, we delete row 1 and column 3. We are left with A1, A2, B1, B2. And then what happens next is you find the determinants of these small matrices. So you are going to continue further and solve. So you're going to have I into A2. So you're starting with the leading diagonal minus the other diagonal, A2, B3 minus A3, B2. So J will be A1, B3 minus A3, B1 plus K, A1, B2 minus A2, B1. And kindly note that A cross B is not equal to B cross A. Instead, one gives a negative of the other, because so here you're going to get, if you're having A cross B, it's equals to minus B cross A. Interchanging the rows results in a change on the value of, on the coefficient. If it was positive, it becomes negative. So let's handle a practical example so that you can see what happens. So we have an example here. We have vectors u is equals to, so you're going to use u and v. You can use anything you want. So our vector u is 2, 1, negative 1. Our vector v is negative 3, 4, 1. So you're going to arrange. If you have to get A cross B, you're going to start with I, J, K, and then it's A cross, no, this is going to be U cross V, because you're using U and V. So we have 2, 1, negative 1, negative 3, 4, 1. So we are doing exactly what we did before. We cover 1, then like that. So we're going to see, we're going to have I into, so if you cover 1 and this, you're going to get 1, negative 1, 4, 1, minus J into, if you cover these and the first, you're going to get 2, negative 1, negative 3, 1, and now plus K, you're going to have 2, 1, negative 3, 4. And remember, the straight lines denote okay, wait first. So we have, you're getting the, using the diagonal. So we're saying that name has disappeared, sorry. So we have I into, we have 1 minus 4, which is 5, minus 2 minus, so this gives us 2 minus 3 is negative 1, and then this one is negative, so it becomes plus J, and then here we have 8 minus, so it becomes 11K. So here we are going to get 5I plus J plus 11K. So this is not a normal matrix. There's something we are getting, but the name has disappeared. So that is what you get after finding U and V. So here we have, let's see what else we have. So we have an alternative method of getting that, but now, so that alternative method is quite easy. You don't have to get I, J, and K separately. So we're going to write the formula first. It's called the rule of Sarus. The determinant, oh yeah, I've remembered. So here you're getting the determinant. So these straight lines you see here denote the determinant. That name had disappeared completely. So here you're going to write I, you write J, you write K, and then you have A, B, C. So you have A1, A2, A3, B1, B2, B3. So what happens with this rule of Sarus is you copy the first and the second. So we have I, A1, B1, then J, A2, B2. So you copy everything, the first column and the second column, you copy them. And now we go like this. So you go like that. So on the leading diagonal, the products we are adding. So just the same way you get a determinant for a 2 by 2 matrix, you're using that concept. So this one is adding, adding, adding. On the other diagonal, you subtract. So this will be minus, this will be minus, this will be minus. So you write here, you start with the leading diagonal minus the other diagonal. So you're going to have I times A2 B3. So we have I A2 B3 plus, we are adding, this is J, this was A3 B1, J into A3 B1 plus K into A1 B2, and now minus. So we are minusing, we are subtracting. So we have K into A2 B1. So since you're using a bigger bracket, you can just add here, because after all this minus will influence all the others. So here we have I into A3 B2 plus J into A1 B3. So that's basically the formula, A1 B3 or B3 A1. So you are going to collect the like terms and then you subtract. So the i's will subtract with the I, the j subtracts with the j, and the k subtracts with the k. So if we're going to use our previous example the way it is, so our previous example is here. So we have 2 1 negative 1, and then v is negative 3 4 1. We're going to use that with this rule of Sarus, and it's called the rule of Sarus because of the inventor was called Sarus, of getting determinant without having to use the cofactor method. So this is the rule of Sarus. So let's see our previous example. So if you're getting A cross B, we have I, J, K. Previously we had 2 1 negative 1 3 4. We had 3 4, and our other value was 1, was negative. We had negative 3 4 1, negative 3 4 1. So you write, then you start again, I 2 negative 3, J 1 4. So you do the same thing, like basically. So you're going to have I j k. The leading diagonals are adding, and then you're going to have k I and then this one is for j. So you will have 1 times I is 1i, plus negative 3 times negative 1 is 3j, plus 8k, minus sorry, we have minus 3k, and then this is 4i, but now, so we are subtracting, so we have minus, and then this is, so we have minus plus minus 3 minus 4, sorry, minus 4i plus 2j. So if you collect like terms, 1i goes, this is minus minus, so this will become plus. So we're going to get I plus 4i plus 3j minus 2j becomes just j. 8 minus minus becomes 11. We're getting the same thing. So we have 5i plus j plus 11k. And now remember, you have to indicate that they are vectors. So that's how you get. And remember, we say that a magnitude is the same as length. So we're going to prove one simple property, and then that will be it for vectors. So our next will be on projection. So we have a question here, an example. Prove that A cross A will give us a 0. So our first step is to define A. We are going to say that A is A1, A2, A3. So we're going to write it down. Going to have A cross A. We have I, we have J, and we have K. So we have A1, A2, A3, then A1, A2, A3, because it's A by A. So you block the first part, you're getting I into A2, A3, A2, A3, minus J. If you block the second column, you're getting A1, A3, A1, A3, plus you have K. If you block the third column, you're getting A1, A2, A1, A2. This simply gives you a 0, because you're going to have, for instance here, A2, A3 minus A2, A3. That's 0. So anyway, we're going to have A2, A3 minus A2, A3. This is I minus A1, A3 minus A1, A3. plus k. We have a1 a2 minus a1 a2. You can see that everything is 0, so you're going to get 0i minus 0j plus 0k, which in simple terms is just a 0. So that's it for today. But before we go, remember we have some properties of cross product. We have that if a given I cross j is equals to, not I cross j, I cross I is equals to j cross j is equals to k cross k is equals to 0. So the other properties are quite easy and can easily be followed through. That's why we have left them out. Thank you for joining us today. Kindly stay tuned because we have one more thing to handle, which is the projections and directional cosines. Thank you and bye.